So in the last video, we took a look at our model for static friction. And here we're going to take a look at kinetic friction and talk a bit about rolling friction and how that differs from static friction with wheels. So anyway, let's take a look at kinetic friction first. So first, this model is much more straightforward. Kinetic friction is where the two surfaces are sliding with respect to each other. In this case, the direction of kinetic friction will always be to oppose the relative motion of the two objects. So say you go ahead and you just kick a pebble or something like that, and it's skittering along the sidewalk. The force of kinetic friction between the sidewalk from the sidewalk acting on the pebble will be against the direction it's moving. It can get a little trickier if we think back to our truck and crate. If the crate were slipping out the back of the truck, so thinking again about where the truck was accelerating forward. If it was accelerating forward so hard, and say the box is made of Teflon or something like that, where it's a very slippery surface, what you might find is that the required force of static friction wasn't big enough compared to the maximum value, in which case it would begin to slip. Again, by Newton's first law of motion, the crate would be moving forward, but it wouldn't be moving forward as fast as the truck because the truck's picking up speed. So the crate would be sliding backwards relative to the truck bed, even though they're both moving forward, but that would still mean that kinetic friction would point forward in that case. So it's always the relative motion. It's easiest if you can just imagine yourself sitting on the surface and thinking about which way it's sliding if you're just sitting on the surface watching it move. Okay, now if it is sliding, the direction is always to oppose the relative motion, and the force of kinetic friction is always modeled to be equal to the coefficient of kinetic friction. So this is still that same letter mu, now we just have a k, times the normal force. So this is actually a lot easier than static friction, in my opinion. In static friction, you pretty much always have to do Newton's second law to solve for it, and then compare that up against Fs max to see whether it's slipping or not, unless you happen to be given code words to tell you that the force of static friction in that particular case just happens to be Fs max, but that's not usually a guarantee. But here, it's just the coefficient kinetic friction times the normal force. And these coefficients don't have units. The normal force has units in newtons, so does the force of kinetic friction. So the coefficient itself is dimensionless. All right, so let's just work a quick example of this. So let's just say we've got a crate that is sliding along the floor. Let's say the coefficient of kinetic friction between the crate and the floor is 0.5. Let's say it's initially going at 20 meters per second, and it eventually skids to a stop over here. And what we'd like to know is how far does it slide? So again, we can do our same trick here. We can say that we can set x initial to be 0 here and say that this really amounts to solving where x final is located. So just from that alone, this is going to be another one of those cases where you are going to think backwards and solve forwards. So thinking backwards, you're going to look at this and say, oh man, this really looks like kinematics. And your instinct would be to solve it with kinematics, but then you go and look at it and you realize you're being asked to find x, so okay, that's not missing. You are given v final, that's not missing. What you're not given is you're not given the time and you're not given the acceleration, so doggone it, you're missing too many things. So this means you have to go back a step and either get yourself the time it took to slide or the acceleration. You look at this and you think, well, in the problem they gave you the coefficient of kinetic friction. That sounds a lot like forces, so I'm going to guess that we use Newton's second law to solve for the acceleration. Then, once we use that to get us the acceleration, we'll be able to use the missing t kinematics equation to get ourselves the distance traveled. So let's go there. So I'm starting by doing a force identification diagram. So we put a circle around our system, and we see where it cuts through the surface that we're going to have a normal force, and since it's sliding, we're going to have a force of kinetic friction since it's actually sliding. Then we ask if there are any long-range forces, and yeah, it's the usual suspect, gravity. All right. So, and once again, yeah, I didn't give you the mass, did I? And again, that's the sort of thing where that can sometimes happen. And if that happens, you just have to hold your nose and hope that it cancels. And this is where working in letters rather than numbers can give you a big payoff. Okay, so let's go ahead and draw our free body diagram for the problem. So there's our crate, normal force up, gravity down, kinetic friction off to the left. And I put kinetic friction off to the left because unlike tires, these coefficients of kinetic friction generally tend to be less than 1. All right. So since it's less than 1, we expect that the coefficient's less than 1. We expect that the force of kinetic friction will be less than the normal force. So that's why I drew it shorter. All right. We're going to go ahead. Normally, I would be tempted, because the object's accelerating to the left, I would be tempted to make the x-axis point left. But here I'm not going to, and this is because we've got a bigger kind of requirement here looking at the kinematic situation here. We've already kind of tacitly put the x direction to the right. So it's probably better if we just do it like that. So here we'll go ahead and say that this is the plus x direction, that's the plus y direction. And so we can go ahead and express Newton's second law here. So F net equals ma. And since my acceleration is unknown, what I'm going to do is I'm going to pretend that a points right. We know it really points to the left. I'm going to pretend it points to the right. This is going to give me a negative value, so that when I plug it into the kinematics, the signs work out. But in a situation like this, if you get yourself flustered by the signs, it's okay to just use your common sense and realize that when you plug into the kinematics relation, that better end up being a negative value that goes in. And so if you got your coordinate system or your signs turned around somewhere, that can be an easy fix to do later. All right, so let's do our vector sum of forces here. So this will be the normal force plus gravity plus the force of kinetic friction equals ma. And we'll start by taking the y components of all that. So that'll be ny plus fgy plus fky equals may. Now a sub y is 0. So we can put that in right away. And similarly, fk acts only in the x direction, so that's 0. So we'll put that in right away. All right, looking at the rest of this, the normal force points entirely up, so we can just say n. Gravity points entirely down, so we can say minus fg. That equals 0. So you get that the normal force is equal to fg, so it's equal to mg in this case. All right, now let's go to the land of x. In the land of x, like I said, keep in mind I'm pretending that the acceleration is pointing to the right, thinking ahead to when I'm plugging into the kinematics. But however you want to do it is fine, as long as you realize at the end of the day it's really going to point to the left. So here, normal force and gravity both act purely in y, so they're both 0. The force of kinetic friction points purely to the left, so it'll be minus fk. And here we're just going to say ma. So the acceleration will be minus fk over m. And it sounds like all might be lost until we remember that our model of friction is that this will be minus mu k times the normal force over m. So we can plug in here. Say a is minus mu k. That's just awful. Minus mu k. The normal force we worked out was mg over m. Cancel, cancel. You get that this is minus mu k g. Hey, all right. Well, g has units of newtons per kilogram, but that's dimensionally the same as meters per second squared, so we're good there. And like I say, we got our minus sign, so I can just plug that right into the kinematics equations, where the kinematics equations always sort of assume it points right until you plug in the minus signs later. Okay, so now that we've done that, we can go ahead and stick that into our missing t kinematics equation. So that will give me v, that's a terrible t. So that will give me v final squared equals v initial squared plus 2a x final minus x initial. All right, we can put in the things known to be 0. We know that the crate slid to a stop, so v final was 0. And following our usual tricks, we set x initial to 0 just to make it easier to solve for delta x, because this way x final is delta x. All right, so doing some algebra. 2a x final equals minus v initial squared. So x final equals minus v initial squared over 2a. Alrighty. So again, this might look bad because we've got that minus sign there, but remember the acceleration points to the left, so that minus sign is going to go in to take care of it. So I have minus v initial squared over 2 times minus mu k g. Cancel, cancel out. That's all good. All right, so sticking in our values, we will have 20 meters per second squared over 2 times our coefficient of kinetic friction is 0.5. Oh, isn't that convenient? It's almost as if I'd set it up that way. Times 9.8 newtons per kilogram. And we remember that newtons per kilogram are dimensionally meters per second squared. So when I squared the 20, remember it's all, you have to square the units too. So this will be 20 squared, meters squared over second squared. So my second squareds cancel and I'll lose 1 power of meters. So sure enough, I'm left with meters and I have 40.8 of them. You might ask yourself, does that sound reasonable? Well, something moving at 20 meters per second is moving on a good ways. Is moving on a pretty good clip. So you might expect it to go skidding for a while. So yeah, that seems perfectly reasonable. Alrighty. So I'm going to take this opportunity here to give a bit of an aside about rolling friction and how tires really work. So again here, rolling friction also opposes the motion. You can write Fr equals mu Rn, and it works just like kinetic friction. But the thing is that usually these values of mu R are really small. So usually you can just neglect this altogether. I mean, there are times where you can't. If you're designing a car, you definitely can't. Bike tires, basically inflatable tires, you can't. Kind of wheels on a shopping cart, maybe you can get away with it. So anyway, what's going on here? So the first thing to ask yourself is, in normal operation, what force is actually making a car go forward? Think about that for just a second. Okay, you're probably going to hate me here, but it's actually static friction is what makes the car go forward. And probably the easiest way to remember that is to say, a car goes forward because of tires roll forward because of static friction, WTF. All right, so why is this? So greatly exaggerated here. I'm trying to draw what a tire looks like. Now here, if you looked at your tire, at your car tire like this, you'd be going, oh geez, I need to get some air in those tires right away. I hope I didn't pick up a nail or something like that, right? But even when they are inflated properly, the bottom of the tire is actually flat. And this flat strip, where it's in contact with the road, is cleverly called the contact patch of the tire. Now, when the tire is, so let's say the tire is rolling like this so that it'll be moving forward like that. You're going to, if this is attached to a car or something like that, there's going to be air resistance pushing against the tire or pushing against the car. So you're going to need something to be making it go forward. And if you do your force identification diagram for this, we'll note that rolling friction is there, but we won't stress about it just yet. So we go and do our force identification diagram. It's going to be the same deal. There's a normal force here. There is a force of static friction. And the reason it's static friction is because these surfaces aren't moving. They are stationary. It's, it's only if you're skidding out that it's kinetic friction. These surfaces are stationary. In fact, as the tire rolls forward, it leaves behind about roughly a 1 molecule wide layer of tire behind it, basically permanently. So you can actually pretty accurately think of a tire as acting like a roll of double-sided tape. And this double-sided tape does a better job of sticking to the road than it does to the adjacent layers of the tire. So as you drive along, you lay down molecules, you lay down tire compound here, and you end up getting a buildup of tire material in the back. You'll sometimes notice this, on a freeway, especially if it hasn't rained in quite a while. You'll start to notice dark patches where the cars are driving. That's leftover tire rubber. And we'll go ahead and just for the giggles, we'll put in rolling friction, but we'll get to that. And then you ask what are the long-range forces? Yep, you guessed it, gravity. So when we draw this, we're going to have, and then, oh yeah, since this is attached to a car, we'll also note drag from the car, since the car is attached to it. So when we draw this, we're going to have normal force, we're going to have gravity, we're going to have drag here, but even for us to go at a constant speed, something has to make it go forward. I've already said that rolling friction is going to oppose the motion, and with the exception of car tires, that's usually negligible. So it turns out that static friction has to point forward in order to make the car go forward. And it is static, again, like I said, because this contact patch literally it's stationary with respect to the road. It's like a piece of tape unrolling. So that's another one of our WTF moments. Static friction makes the car go forward. WTF is pretty much how I remember it too. Okay, so what's going on with the rolling friction bit? So some texts out there make a deal about the rolling friction, and it only really matters with car tires, especially when you're at slow speed, where with modern streamlined designs, you can get to a point where drag is less than the force of rolling friction. So when drag, oh, by the way, before I forget, this is also why you tend to see more tire buildup in front of traffic lights, because there the car needs to accelerate forward, requiring a bigger force of static friction forward. You tend to lay down a bigger, you tend to lay down a little more rubber there. All right, anyway, moving on. So what's going on with the rolling friction then? So there's two sources for it. The small source and the big source. And we'll get to this. We'll do the small source first. So again, drawing one of our greatly exaggerated tires where I'm trying to draw in a contact patch here. Since you're leaving behind tire here, what is going to happen is right in here, you're going to be having to break molecular bonds between the compound being left behind and the compound still on the road, or still on the tire. So some of that is going to work towards giving you a force backward. So that's part of your rolling friction. The other bit is the making of the contact patch in the first place. Because if you think about it, the tire would like it if its shape went underneath the road. So if you look at, like, say, this chunk of tire right here, as it rolls in, it actually kind of collides with the road. And it's going to feel a normal force from the road kind of doing one of these numbers. And so most of that's accounted for in the vertical normal force, but there's also oppose the motion effect that comes into play. This is part of why tire inflation pressures are themselves a bit of a black art. Generally speaking, the harder you inflate the tire, the less of that you have going on, but then that's at the cost of good handling and stuff like that. So it depends. So again, there's a whole trade-off of engineering design considerations into picking the appropriate tire compound and figuring out what the appropriate inflation pressure would be. So again, like I say, I don't typically make too big of a deal with rolling friction. If you look at like a solid wheel or something like that, yeah, it's there. Is it a lot? No. So like the wheels on a shopping cart or something like that, you don't really have to get too stressed out about those. It only really shows up when the deformation is really big. So like, car tires or something like that. Then that's where you have to take it into account. So this is always part of the trade-off in design. If you're designing a vehicle for high fuel economy, there are you wind up having to worry about two things. At freeway speeds, the drag will dominate. But as you make the car more and more and more aerodynamic, what will happen is that when you get to, say, a little slower than city driving speeds, or maybe even typical city driving speeds, depending on how bad the traffic is, the drag has gotten low, and we'll get into our models of drag in the next video. But the force of rolling friction is still there, and that becomes one of the big sources of inefficiency that you may have to worry about if you're trying to design a very efficient vehicle. But anyway, enough with that. In the next video, we'll go ahead and take a look at drag and do maybe another example or two. Catch you in the next one.